All right. Now, just to recap, so we are going to simulate this combustor. So there's a mixture of air and natural gas from below here. So, and then all the dimension, you can refer to my PowerPoint slide later on. Yeah, all these have all the dimension. And you need to go back and read a little bit about these slides, about the problems, description, and so on. All right, we're back to our ANSYS. So yeah, before we start, we need to use the Fluent. And then you save this project. So let me find my file. So I'll save this one as non-premixed. All right. Then after that, you already saved your project already. Then go to setup. So after that, because we are using a 2D file, so go to 2D, double precision and serial. Make sure the display mesh is activated. Click OK. Does the video more smoother? I mean, able to see the update on my screen?
Yes, sir.
Okay. Now, after that, we're going to import the mesh file from non-premixed. So let me go and find my file. Okay, download this file, bel.mesh mesh file. So you upload into your PC there. So yeah, so before this, you will see some information on the console there. So the first one, you will see that there's 9,784 quadrilateral cells. Yeah, so if you're using a student version, there is a limitation on the cell, right? And then in the console there, just now we see all these warning. You see this show you some warning. It asks us to advise us to change to asymmetric. So later we're going to use asymmetric setting. All right. So after that, before we do anything, we need to check our mesh. So click and check. So make sure the minimum volume is positive. And then we're going to scale this mesh file. So go to our mesh is created in mm. We're going to view our length unit in mm. So after that, click scale. So you'll see that the maximum X is 2989. The Y max is 533.4001. Then click close. So after you click mesh, it's always good practice to check the mesh again. So the minimum value have to always have a positive value. Okay, we're done with our mesh. Then we're going to set up our domain here. So we go to result here, which we already done already. So result graphic, right click, view. So this one, because we need to select the mirror plane, we need to mirror this mesh file. So make sure if you see 0/1 means nothing selected. So we're going to select axis 2, and then after axis 2 selected, click apply. So you'll see it mirror to another side, then close this one. Okay. Then we're going to set up our system. So the one, you go to general, and then make sure you select the asymmetric swell, this one, and we will go to use pressure-based solver, time steady. So once you select all this general, you go to model, activate the energy on, and then we change the viscous equation from laminar to K epsilon, and then we use all the standard setting at this moment. Then click OK. Then after that, under radiation, go and radiation edit. So we're going to use a discrete ordinance. So click this one. So you open up this one. So just now we stop at here. So make sure when you open up the radiation model, you are selecting discrete ordinance, DO. And then change the energy iteration per radiation reduce to 1. Reduce to 1. And then once you click OK, you will see this warning come out. Please confirm the property values before continuing. OK. Then after that, we're going to select a non-premixed combustion model in species. So go to species, right click, edit. So under species here, we're going to select non-premixed combustion. So this is the main topic of this exercise. So we go to species here, select non-premixed combustion. Then after that, we will enable the inlet diffusion in the PDF option. So here in the PDF option here, activate the inlet diffusion. And then the next we will define our chemistry model. So this is the chemistry model. We will use the chemical equilibrium, and we will retain the operating pressure, which is our standard atmospheric pressure, 101. For this one, field stream reach familiarity limit, we will increase this number. Field stream reach familiarity unit limit, we will increase to 0, we will lower, sorry, 0.064. Key in 0.064 for the field stream reach familiarity limit. So what does this number allow you to do? So this one, the number 0.064 enable you to perform a partial equilibrium calculation. So and then it will increase the efficiency for the PDF calculation, allow you to bypass a complex equivalent calculation. All right. So this number you can play around. If you're not able to reach equivalent equation, you go here and change this number. Okay. The next one, we're going to set up the boundary. After you change the chemistry properties, you click the boundaries. So here we need to monitor the species, the combustion product that we have. So for this one, you need to go to here. We need to add a species inside this table. So go to boundary species there, key in C2H6, key in C2H6. All right, then click add. You will see C2H6 added in the table above. Okay, are you able to follow up to this stage?
Yes, sir.
All right, so C2H6 added, you need to add another 2 more. C3H8. Okay, the next one is C3H8 and then add into the table. C3H8, add in the table, and then add another one, C4H10. C4H10, add into the table, and then add one more, CO2. CO2, carbon dioxide, add into the table. So in your table, you should be seeing additional species added, C2H6, C3H8, C4H10, CO2 in the table.
Oh.
Done?
Question. So we are adding the C3H6 because we're going to use it.
Yes, because all these species was not inside the non-premixed combustion by default. So you need to add this chemistry or this byproduct inside this table.
Okay, so that means if we want to add the chemical, we have to go through under the species.
Yeah, under boundary species, add in the number, add in the name here. Okay. All right. So the next one. Okay, the next one we're going to change the specified species in. We're going to use mole fraction rather than mass fraction. We're going to use mole fraction. Right, we're going to use mole fraction, activate mole fraction. There's a difference between mass fraction and mole fraction. Today we're going to use mole fraction. Have you changed this one?
Done, sir. Done.
Okay, done. So if you look at the table, we go slowly, one by one. So if you look at N2, nitrogen, and O2, this is our oxidizer, oxidizer. So if you roll up, there's an oxidizer and fuel. So to make a combustion to happen, you need two elements. One is oxidizer, one is fuel. Oxidizer means the element that create oxygen or the burning element to the combustion process. So if you talk about combustion, you have two elements. Two big family. One is fuel, one is oxidizer. So in this case, you see oxide and fuel. Oxidizer. In this case, you are seeing nitrogen and oxygen. We will use back this number, so you don't need to change anything at this moment. So what is this number mean? 0.789. It means you have about 79% of nitrogen and 21% of oxygen for the oxidizer element. You add these two together, you get 100%. Okay, that's why we use a mole fraction here. Okay, mole fraction means percentage. Okay. Then the next one, you're going to change something on the mole fraction here. So we go to CH4, we will change 0, we will keep updating number. The first one, you go to CH4, we will change 0.6, 0.965. N2, then you go to N2 here. N2, we will add a little bit of nitrogen there, 0.013. So you update two number. One is CH4. Under fuel, you add 0.965. For nitrogen, N2, you add 0.013. Okay, the next one, you roll down. You go to C2H6 that you just added, C2H6, to change the number to 0.017. C2H6, you update the number to 0.017. C3H8, you update the number to 0.001. C4H10, you update the number to 0.001. Carbon dioxide, you update the number to 0.003. So make sure you see all these number in the species setting under field column. Under field column. So you actually are changing C2H4, C2H6 0.017, C3H8 0.001, C4H10 0.001, CO2 0.003, and one more just now you change, two more you change just now. CH4, the fuel is 0.965, nitrogen is 0.013. Understand? Huh? Have you done?
Done, sir.
Okay. So again, all these are percentage. For example, carbon dioxide, if you put in 0.003, it means that you have 0.3% of carbon dioxide. Okay. If you still don't understand, you look at the oxidizer. Nitrogen 0.789 means about 79%. So oxygen is 21%. Okay, make sure you understand all this number. All right, then the next one, we're going to change the temperature for fuel and oxidizer. So we need to change the both into 315. Fuel and oxidizer increase the temperature to 315. So this one was mentioned in the setup or in the question itself. So change this temperature to 315. Are you able to follow?
Yes.
Okay, then next you go to the top here, click the table. Click the table and then make sure the automate grid refinement is activated. There's a tick there. Then we will use all the default number at the moment. Okay, after that, you click this one, calculate PDF table. Click this one. So you will start calculating, you'll see something happen to the console. You will start calculating for the PDF number. And what is this process about? Is you'll compute the non-adiabatic PDF table. So you will see at the console, at my console, you see that 2252 points calculated, 20 species added, and PDF table successfully generated. So at the background, there's some data generated already for the species process, for the combustion process. Do you see this one in your console?
Yes.
All right, so then next one, there's a click here. You can click display PDF table. Click this one, click display PDF table. All right, so you'll see a table pop up. So we will reframe all these parameters at this moment. So you click display. You'll see something happen in your graphic window there. Okay. Are you able to see this graph?
Yeah.
Yeah. This actually is a 3D graph that you see there's a lot of different axes there. So you see a scale variance, you see a mean mixture fraction, you see a scale variance, and at the back there you see there's a mean mixture fraction. And if you rotate, if you try to left click, hold your left click and try to move around, you see that the graph actually is a 3D profile. So this graph is a mean temperature graph for our combustion process. It's in a 3D form. Okay, once you're done, you just close everything, close all the window that you have. Then after that, we want to save the PDF, all the data. So you go to File, Export PDF. Go to File, Export PDF. And let me find a place for me to save. Okay, I will save this one as bl.pdf. Oh no, bl1. We have one first scenario. bl1.pdf. Then I will save this exercise. Okay. Of course, later on, the file, although it is a PDF file, it's not a normal PDF. It's not the normal PDF that we see. In this ANSYS, the PDF file means it's a data file. If you if you use the normal software to open, you will see a lot of text inside there rather than the graphic. So this is the PDF file. This is the graphic that you see. This 3D graph is the PDF file. It's the contour of your data. All right, now we have done the setup for our models. The next one, we're going to set up our material. Okay, so I will just minimize all the three that not relevant. I'll go to material here. I'll expand my material, set up materials, and then under, let me see. Okay, so you need to double click the material and you will see the material page come up. Do you see this one, the task page?
Yes, sir.
Yeah. So I want you to highlight the PDF mixture, left click, after that you click create edit. You will see that the create edit material window come up.
Yeah.
The name is a PDF mixture. Yeah. So you go to the property window here. We want to change something here. You roll down. There is absorption parameter. Let me see here. Absorption coefficient. Where is it? Here. All right. Go and select this one. Absorption coefficient. Expand this one. Choose WSGGM. WSGGM domain base. Select this one. Okay, so for absorption coefficient, select WSGGM domain base. After that, click change or create. Click this one.
What is WSGD?
Is a okay. The long name for this one is weighted sum of gray gases. Weighted sum of gray gases is a chemical equation. All right, is a chemical composition equation. WSGGM is a weighted sum of gray gases model.
So why are we choosing domain?
Again, your question?
Why are we choosing domain?
Yeah, correct. It's a domain based.
Yeah, why are we choosing domain?
Right, because we want to use this model because we are simulating a non-premix scenario. So that's why this come into place. For this scenario, for the absorption coefficient, we will use this model. Yeah. All right. So once you click the created, all right. Once you created, then you can close this one. All right. You already created the properties already.
Yeah.
Next one, we go to boundary condition. So boundary condition, we want to set up our boundary condition. So before that, we need to read a file. We need to read a file from the Moodle again. So go to file. You need to read the berl.profile.prof. File, read profile. You go to file, read profile, and then go to the file that's now. So there's a BL profile there. Select this file. BL click OK. So you will load the profile inside the simulation.
Okay.
All right. Then we start to set up the boundary condition, on the tree here. So the first one we going to pressure outlet number 3. So pressure outlet number 3 is P outlet 3 pressure outlet ID 13. Click this one, or you can double click. So open up the pressure outlet number 3 there. Then you will see the window here. So what we need to change here is go to turbulence model setup. Here we will change the method to intensity hydraulic diameter. Intensity remain 5. However, the backflow hydraulic diameter we will change to 600. This one, it will change according to the diameter of the profile. So you can see here, this is your pressure outlet. You see here. Mac flow. Here is 300. We key in 600. There's somewhere here. Our DO. Okay, we will come back to this diagram. So at this moment, we key in 600 for the hydraulic diameter for outlet number 3. Then after that, we will go to thermal. After you set up the diameter for outlet number 3, 600, then you go to thermal, we increase to 1300 Kelvin. For the backflow total temperature, we will key in 1300. Then after that, click OK. So we already set up pressure outlet number 3. Then after that, we go to air inlet number 4. Air inlet 4, this one. Air inlet, that one. We will go to this velocity specific method, this one. We will change to component. So velocity specific method, change to component. Then we go to axial velocity, this one. Axial velocity, you go to constraint there, drop down, select velocity profile U. Velocity profile U means the velocity in the x direction. Okay, velocity in the x direction. Then after that, in the swirl velocity here, also swirl velocity, you go to velocity profile W. This one is in the z direction. So swirl velocity is according to the velocity profile at z direction. Then in the turbulent window here, specific method here, also we need to change it to hydraulic diameter model. Turbulent intensity will increase to 17%, 17. And then the hydraulic diameter reduced to 29. All right, so the next one is thermal. Once you set up all this number, go to thermal. Thermal change to 312, temperature Kelvin, 312. After that, you click species. Are you able to follow?
Yeah, yes, sir.
Yeah, so now we are at species. So species here, we will set as 00 for at the moment. For inlet, because the inlet, there's no mixture yet. So these two value is 0. Right? Okay, then click OK for inlet number 4. Then we go to inlet number 5. Inlet number 5 is our fuel inlet. So go to fuel inlet 5. So fuel inlet number 5, we need to set up the fuel parameter there. So fuel inlet, we will change for the momentum. For velocity specification method, we change to component. And then you go to radial velocity for our fuel inlet. Radial velocity, we will key in 157.25 for radial velocity. Turbulent intensity, we use the 5%. And for turbulent viscosity ratio, we use 1.8. No, sorry, we need to change this one. Specification method, we need to change to hydraulic diameter. Hydraulic diameter, 5%. And the diameter will be 1.8 mm. Right. So this hydraulic diameter, we set the double the height of the 2D inlet stream. We double the value over here. Then after that, we go to thermal. Click the thermal. We key in the thermal 308 Kelvin at thermal. Then go to species. Species, because our inlet field there, we will key in mixture fraction to 1. We'll increase, mean that at inlet number 5, the field start to have mixture process. Then click OK. We set up the inlet number 5 already. Are you able to follow?
Yes, sir.
Okay, now we go to wall number 6. Wall number 6, you double click wall number 6. We're going to edit the wall number 6. So we want to change the temperature for the wall number 6. Go to thermal, temperature. Change the temperature of the wall 1370. Internal emissivity change to 0.5. Okay, so for wall number 6, thermal temperature will change to 1370. Internal emissivity we change to 0.5. Then click OK. We have set up for wall number 6. Then after that, we will change all this value. We will change the value for the wall 8, 7, 9, 10, 11, 12, 13 according to this table. All right. According to this table, but I'll still show you according to this table. So temperature we will change to 120, intensity to 0.5, 135 to 0.5, and so on. Okay, we'll do these steps. Huh? Okay, so just now what we do is that we set up for wall number 6 just now. We already done wall number 6, so wall number 7. Now we do wall number 7. So set up wall number 7, go to thermal, temperature. Change the temperature for wall number 7 is 1312. Internal emissivity 0.5. Okay, once you're done, click OK. Have you done wall 7?
Wait a second.
Wall 7. Go and set up boundary condition for wall 7. Temperature 312. Internal emissivity 0.5.
Done, sir.
Okay. Later you need to show me your screen. Huh? Okay, if you're not able to follow, let me know. Now we go to wall number 8. Set up wall number 8. Again, thermal again. Temperature. Change the wall number 8 temperature to 1305. Internal emissivity, again we use 0.5. Wall number 8 temperature. Wall number 8 go to the thermal. Set up the temperature at the wall number 8. Temperature is 1305. Internal emissivity to 0.5. Then click OK. Have you done wall number 8?
Done, sir.
Okay, then we go wall number 9. Again, go to thermal temperature. Wall number 9 is a little bit special. We need to plot according, the temperature will according to temperature profile. So you go to temperature, beside there, there's a constant drop down. We're going to use the temperature profile of T. Select this one. Yeah? For thermal, for wall number 9, we will use temperature profile T. Internal emissivity, we will use 0.5. Then click OK. Have you done wall number 9?
Done, sir.
Okay, then we go wall number 10. So wall number 10 again, change temperature. Temperature to 1100, emissivity 0.5. Then click OK. So wall number 10, change the temperature to 1100, internal emissivity change to 0.5. Then click OK. Have you done wall 10?
Done, sir.
Go to wall 11, edit the wall 11 temperature. Change the temperature to 1273, internal emissivity 0.5. So for wall number 11, temperature is 1273, internal emissivity 0.5. Then
Done, sir.
okay. Wall 12, change the temperature also. Wall 12, 1173, internal emissivity 0.5. Wall 12, temperature 1173, emissivity 0.5. Then go to well 13. Wall 13, thermal, temperature again. Wall 13, 1173, 0.5. Have we done? Then click OK.
Done, sir.
Okay, so we have set up all the boundary condition already. Then we want to plot the temperature for our furnace wall. It is wall number 9. So how do we do it? We go to post-processing. We go to post-processing, plot, and then profile data. Post-processing, plots, profile data. Post-processing, plots, profile data. Then you'll see a window like what I see just now. So from the profile, we want to look at temperature profile rather than velocity profile. We want to look at temperature profile. Y-axis will be temperature, and then x-axis will be x. All right. After that, you click plot, and then you see what happened to the screen here. Plot, you will be seeing temperature on the left-hand side, and then this is a distance from 0.4 to 2.4. So you see that the temperature start from 1100, and then it keep increasing as it go up the chamber. All right, so the temperature goes up, maximum around 12400, then go down a little bit, then go up again. Okay, so this is the temperature profile that we're going to generate. Then after that, we're going to look at velocity profile. So remaining by going to, again, the same window again, processing, post-processing, plots, profile data again. Select the velocity profile. Y-axis is the velocity u. However, the y-axis, the x-axis function is along your y. So select velocity profile, y-axis u, x-axis of your graph is according to y value. Then click plot. So you'll see that as is increased the height of the chamber, right? You see that the velocity is going up to a maximum of 40 meter per second, about there lah, at a section of around 0.034 mm location. All right. So far we see two kind of graph: profile data, temperature and velocity. The next one, we will look at your swirl inlet. So swirl inlet, still the same. You change the y-axis. The swirl, again the swirl speed is W. So change to swirl W. And then remainder, we want to see the velocity profile at the swirl speed along the y-axis. Then click plot. So the axis of the plot will change to W. So the W also reach maximum at around 0.034 mm position. All right, maximum is about 270 about 27 meter per second. Right. So this is how you plot the graph. Right. Close the window. Now we're going to set up our operating condition. So go to setup, and then there is setup boundary condition, operating. Okay, you go to setup boundary condition, and then in the task patch here, there's a operating condition. Or if you cannot find it, you just go to setup physics. There's an operating condition also, same function. You can either go to setup physics operating condition, or you can go to the body condition here, double click. Then in the task page here, there's an operating condition. You will see the same window. So here, we will, let me see. So we will retain, we will use the operating procedure of our atmospheric pressure, 101,325 Pascal. Then click OK. So we will use the atmospheric pressure to our simulation. The next one, we will set up our solution already. So go to solution, we go to method, double click the method, solution method. We're going to use coupled scheme. And then we're going to go to under pressure, right? Under your special discretization, under pressure, we're going to use Presto asprophy model. Presto. Select Presto for pressure. Then the rest we retain the same. Right. So as you can see, the analysis is quite high because most of it are second order. So only today we look at pressure using Presto model. Right, the next one you go to is a equation. Is a equation. The equation name is Presto pressure equation. It's a series of complex equation. But here there's a lot of model that can use for pressure. So here is a Presto function. Okay. Yeah, you can Google it lah. It's like a very big chapter about mathematics, Presto pressure analysis solution. Okay, but for this example, we'll use Presto lah, in short. The next one, you go to control, double click control. So under control, the column number we will reduce to 70. Right, column number reduce to 70. And then for our density under relaxation factor, density we reduce to 0.2. Body force to 0.8. So relaxation factor, you change density and body force. The rest is by default. After that, we go to residuals. We want to monitor our convergence condition. So we go to solving, report residuals. To solving, report residuals, and make sure print to console is activated and plot is activated. And you can see that the convergence criteria is there. So all the criteria is 0.001. Then click OK. So we are ready for our simulation already. So we need to initialize our calculation. Go to initialization, double click, and then go to use a hybrid initialization. Click initialize. You will see something happen to your console. So you will say that hybrid initialization is done. Then we need to save the case file, export the case file, export your case file. So this one, save in here. So this is your bell 1-1.cas.gz. bell BL BRL bell dash one cache case.cz. Click OK. You save this case. All right. So in the console there, if it tell you that it's done, then we can try for run calculation. So run calculation, we're going to run 1,500 iteration, 1500. Then, yeah, the rest we can let it run. So set iteration to 15,000 and calculate. So it will reach convergence. Our previous record is 1,600, 1060 iteration. So it will take about 5 minutes, maybe, yeah, 3 to 5 minutes to finish the iteration. Okay, so we take a short break. Do you need the break or you want to wait?
We take a break.
You can wait, huh?
We take breaks.
Okay, break. So yeah, we come back. We come back maybe 5 minutes. You need
Okay.
5 minutes is up. Yeah, we come back 5 minutes later lah. Okay, see you in 5 minutes. Okay, those viewer, you can fast forward the video to iteration after 1,600 iteration from the graph. We will get a convergence results around that iteration. Yeah, I thought you take a break.
No, sir.
Okay, my data still not yet converged. Okay. Pratibha, are you there?
Yes, sir, I'm here.
So yeah, so we almost finished already. Your computer calculated done already.
It's under 1,000, sir.
Oh, still running.
Mm.
Okay. All right. Still under 1000. Your computer. What is the iteration number now?
1100, sir.
1100. Okay. So maybe I will move forward. So the rest is just producing the results. I just move forward lah. So later you just follow. So it's just the normal producing the contour and all this lah. So I think something wrong with the setting just now. It should get a convergence around 1600. No, 1060 iteration. It should be reached around here. But I'm not sure why today simulation doesn't reach that way. All right, never mind. Let's check our results. You go to post process after you reach. You watch the steps. Later you try. Okay. Right. So you go to post processing. You go to graphic. We want to see the contour. So go to contour edit. So we want to see maybe you see the temperature. So go to temperature, and then make sure you click the fill, and then click display. So you see that the contour temperature is something like this. It looks normal to me. Okay. So this is the temperature profile. As you can see from my computer, from my screen here, the maximum is at the center here. The temperature will be 1980 Kelvin at the center here, and it's a bit cooler, but not too cold. Green color still about 1000 Kelvin, so it's quite hot here. If you zoom in at the back here, then you will see a cold region, blue air, and our fuel coming in here. So you see the flow is coming in this profile, which is okay for our case. So this is how you project the temperature profile that we did like previously. You go to post processing, contour edit, and then go and change the temperature, click the fill, and click display. This is how you project the temperature contour. The next one, you project the velocity contour. Same. You go in here and change to velocity. And velocity magnitude. Then click display. You'll see the velocity contour here. So velocity contour, again, the maximum velocity is at here, red color, at this region. Yeah, so in your report, you should mention this one. You should zoom in and report the location and what's the value. Okay. So this is the velocity profile, the velocity contour. The next one you want to see is the contour of mass fraction of oxygen. So go to contour again and select species. And here you can select a lot of things. So want to see oxygen. So go to select oxygen and click display. So you'll see that you see the oxygen is quite high at the inlet here. And then it start to mix with your fuel and so on. Yeah? Okay. All right. So this is about the max fraction. The next one is okay. So I think you have no problem on displaying the contour, right?
Yes,
you should know how to display, right? Okay, the next one is to get the reporting value. The reporting value, we go to post processing, report, and fluxes. post-processing, report fluxes, and then straight away ask the computer to tell us the value. We can process four type of value there. So in this case, we look at the mass flow rate first, mass flow rate, and then we look at inlet number 4, we look at inlet number 5, and pressure outlet. So we select these 3 and then click compute. You will see all these numbers come out. So what is important is this one, the net result. So this one should be very, very small compared to the total number you have over here. Okay, so it should be around 0.05 and below. So you should always check the percent. Again, yeah, the percentage is below 0.05. The differences means you take this number divided by this number, you get a percentage. So make sure the percentage is very, very low. So normally below 0.05% is a good one.
There it's 10 to the power -7, but here I got 10 to the power -2.
Yeah, so so it should, you get what?
94.04 times 10 to the power -7.
For the net result, is it?
Yeah.
Okay, so yeah, that one you need to check back again. This is maybe because of the boundary condition that you set up just now. Maybe some number you didn't key in the proper decimal place. Okay, but anyway, the step is
All the value is same. Okay.
yeah. Oh, you mean the above number is same, only the
Yeah.
net number is different.
Yeah.
Okay. Yeah, as long as you see the number is below 0.05%, then okay. Yeah, that's how we the reason why we need to generate the flux report is that you see the error in the calculation, make sure it's low. Then after that, we select total heat transfer rate, and then we see what is the number. Select total heat transfer, then click compute, then you'll get some value there lah. So you'll get about there lah. So you have a very high number. So let me see.
6907.
Oh, sorry, for this one, I think I need to select all. For the total heat rate, I will select all the boundaries inside here, and then it will be very low. Okay, and then the surface integral, we want to see the mass weighted average of temperature for our outlet. So we close this one, we go and generate another report. So report surface integrals. We want to look at report type mass weighted temperature and outlet number 3, pressure outlet number 3, then click compute. So the mass weighted average temperature at the pressure outlet there will be 1464 Kelvin. All right. So this is basically how we do it for the non-premix cases. Okay, let me stop the recording.